Hello everyone. The title of this video is Non-Homogeneous Linear Systems of Differential Equations, or DEs, and we're going to be solving a non-homogeneous linear system of differential equations through a method called variation of parameters. Now you may have seen variation of parameters used to solve just singular, non-homogeneous linear equations. And if you recall that, right, the procedure for that is going to be very similar to what we're going to do here as well. So first I'm going to go into the method, right, and develop the method for you. What is this variation of parameters procedure? And then I'm going to go over several examples. Okay. All right. So first, let's talk about the method, this procedure, the variation of parameters method. So we're given a non-homogeneous system, right? Say x prime equals some n by n matrix A of coefficients times the vector x, which is consisting of the functions, the unknown functions of, say, t, right, variable t, plus, and then some vector f with, consisting of other functions of t. So say x, right? X is made up of functions, say x1 of t, x2 of t, all the way down to x sub n of t, right? If matrix A is an n by n, right? An n by n matrix of coefficients, right? Then this will be an n by 1 column vector with the n unknown functions, and function f is just made up of some other functions of t, right? So say f1 of t, f2 of t, all the way down to fn of t. Alright. So the first step in solving a non-homogeneous linear system like this is kind of like how we would solve just a linear equation. Solve the corresponding homogeneous system, right? So just make, and this is, this is not the zero vector here, because if it were the zero vector, it'd be homogeneous. Well, first step is make that, or imagine that's the zero vector. Imagine that that vector f is not there. So we solve the corresponding homogeneous equation or homogeneous system. Which is this, x prime equals just a times vector x. Alright, and hopefully you recall how to do this. Alright, again, if this is an n by n matrix, you should be able to find some fundamental set of solutions, n of n linearly independent solutions. Say x1 vector x2 all the way down to vector xn. Alright, you should be able to find n linearly independent solutions, a fundamental set of solutions, and then the general solution to the homogeneous, right, this corresponding homogeneous, is called the complementary function, or the complementary solution. I'll say function slash solution. That's the general solution to the corresponding homogeneous. So x sub c for complementary, and that's equal to some constant times vector x1 plus some constant c2 times vector x2 plus all the way down to plus some constant cn times vector x sub n. Now another way to think about this is in matrix form, where I'm going to have an n by n matrix where the first column is vector x1, the second column is vector x2, The third column is vector x3 all the way down to the nth column is vector xn, right? And multiplied by the vector with these n coefficients, c1 through cn. c1 all the way down to cm, this column vector of constants. Now this is given a name. All right, so this matrix in which each column is one of the linearly independent solutions to the homogeneous system. This is going to be called the fundamental matrix, right? Because again, the columns of it are from the fundamental set. And in some texts, this is given the symbol phi of vector x, or I'm sorry, phi of t, because every single one of these is going to be made up of, some sort of expression depending on the independent variable. So this fundamental matrix is labeled phi of t. All right, so phi of t, fundamental matrix, times, and then this is just a column of constants, which I'll call capital C, right? And it consists of our parameters, right? Remember, these unknown constants, these arbitrary constants, are our parameters, things we can choose any value for. Okay, so first we find this, phi of t times constant vector c, the complementary solution, the solution to the corresponding homogeneous equation, homogeneous system. Great. All right, then comes this variation of parameters. Vary the parameters. Now the parameters are again c1 through cn, right? These constants. So what's happening is I'm going to let, instead of these be constants, I'm going to let them vary as the independent variable t changes. So I'm going to change all these constants into functions of t, and we get a totally new looking expression here. Instead of phi of t times c, right, a bunch of constants, I'm going to have phi of t, I'm going to have my fundamental matrix times another column vector, but a vector where each component is a function of t. Each component varies with t. All right, and this will be the form that a particular solution takes. Remember, this is the same way you would go about solving homogeneous linear equations. Right? You find the complementary function or complementary solution to the corresponding homogeneous, and then you find a particular solution. Right? And the form of a particular solution to the non-homogeneous will be the following. So say x sub p for particular will be equal to phi of t, right, the fundamental matrix, times, and then they're calling it in the book I'm looking at, vector u of t. Right? Now you can just call it u if you wish, but I'm going to call it, so you know that things are depending on t in here and not just constants. I'm going to call this u of t, where this vector u of t, right, instead of being made up of constants, these n parameters, I'm going to have imagine that the parameters are varying. So I'll say u1 of t, u2 of t, and all these, un of t, all these functions of t make up the components of this u of t. Alright, so if this is the form a particular solution takes, our goal is now to figure out what u of t looks like. And then we'll know a particular solution, because you should already know, if you found the fundamental set of solutions to the homogeneous, you'll know what the fundamental matrix is, this phi of t. Now the goal is to find this u of t vector. Alright, so the goal is find u of t. Alright, and I'm just going to go in general here into our non-homogeneous system, our non-homogeneous equation, and see if we can solve for u of t. All right, so rather than write all the of t's every time, just know that every vector, everything I write has functions of t in it, depends on t. So if x is equal to phi of t times u, right, a matrix phi times vector u, then x prime using the product rule is, phi times u prime, right, plus phi prime times u. Right, I shouldn't put a dot there. This isn't the dot product. This is matrix products. All right, so phi times u prime plus phi prime times u. Now I substitute these into my my non-homogeneous equation here, and we get phi times u prime plus phi prime times u equals, and then a times and then x. Well, the xp here is just phi times u, and then plus f. All right. Now remember, this phi times u if we get things correct here, you should also notice that if we go back and use the fundamental, so we're going to be using the fundamental matrix. The fact that phi, right, this matrix phi is made up of the the fundamental solutions of the corresponding homogeneous. So phi would be a solution of this equation. So going back to the homogeneous, we would see that phi prime can be replaced by a times phi. All right. All right. So I'm using the fact that the phi is made up of the fundamental solutions of the corresponding homogeneous. I'm going to use that, make that substitution. So we have phi times u prime plus, and then phi prime, as I mentioned, is a times phi. And I have a times phi now, times u prime, vector u equals, and then here I have a times phi times vector u plus vector f. All right. And then look, the reason I made that substitution, so hey, now these are gone, and phi being made up of n linearly independent solutions should be invertible. I multiply by the inverse of both sides, we get u prime, multiply by phi inverse, all right, phi inverse, phi with the little minus 1 on it, times vector f. And then for u, I just integrate with respect to t. So vector u that I was trying to find, or that u of t, is going to be the integral of phi inverse times f with respect to t, where basically when you multiply these two matrices, you're going to get an n by 1 column vector, and you're just integrating component by component, right? I'll just say you just integrate component by component. Alright, so doing this in general will help us with all my examples, because now instead of doing all that junk with the varying of parameters, I can just jump to here, and now that I know what u of t is, you'll know a particular solution, and then putting the complementary solution and the particular solution together, we get the general solution. So part 3, you can state then the general solution of the system will be the following. Right? I can replace vector x in my non-homogeneous system with the complementary solution, or the solution of the corresponding homogeneous, plus, and then a particular solution which has that form there, the phi times u, where u, right, u is this integral of phi inverse times f with respect to t, where you go integrate component by component. Okay, but that's huge there. I'm going to come back to this a lot. Right? And then if you'd like, this is phi times that vector of constants c I called earlier, plus, and then here phi times u of t, where again u is this integral. And I just make that replacement. All right, so lots of stuff here. All right, it took about 15 minutes to talk about that. But now that I've got this down in general, for any, this is for any non-homogeneous linear system, what I just did here. Now we can apply this to several examples. Okay. All right, so my first example, and all three examples I have in this video, I'm asked to do the following. All right, and I'll actually keep this u of t up here, this formula. So I'm asked to do the following. Use variation of parameters to solve the given non-homogeneous system. So the first one, dx dt equals 3x minus 3y plus 4. And then dy dt equals 2x minus 2y minus 1. Right? We're trying to find functions x and y, functions of t that satisfy both equations. I think it would be easier to start off by looking at this as a matrix equation, right? Putting this in matrix form, where I have vector x prime, right, made of components x prime, y prime, equals some matrix where this matrix has the coefficients of x and y. So I'm just looking at the x and y terms here. Down the first column, the coefficients of x, 3 and 2. Down the second column, the coefficients of y, -3 and -2. So that's that's the matrix A. Right. And then times vector x, which is made up of the functions x of t and y of t, and then plus the vector with the stuff left over that doesn't have a function x and y attached to it, 4, -1. Just the vector with these constants, 4, -1, and that's the vector f, right, which is again non-zero, making this a non-homogeneous system. All right, so I'll bring this u back when we talk about the variation of parameters. But the first thing is to solve the corresponding homogeneous system. Right, just get rid of the f vector and find the complementary function, right? The complementary solution, that x sub c. So the corresponding homogeneous system. I'll just put corresponding homogeneous. So that'd be x prime, vector x prime equals matrix A times vector x. And hopefully you recall how to do this from previous videos I have put out a series of videos on solving homogeneous systems. Remember, you find the eigenvalues, right? So we're going to find the eigenvalues and then their corresponding eigenvectors of this matrix. Right, so eigenvalues of A. So that's where I'm solving this equation. When is the determinant of A minus lambda I equal to 0? And each of my examples is going to just have 2 by 2 matrices to make this go by a little faster. So A minus lambda I, I'm just subtracting lambda down the main diagonals. And then everything else stays the same, -3 and 2 there. And this would be, if I multiply these two, I'd have lambda squared, then plus 2 lambda minus 3 lambda, that'd be minus lambda, and then minus 6, and then plus 6. All right, when I subtract -3 times 2, so I got minus 6 there, and then minus -6, plus 6, 0. So this is just lambda squared minus lambda, which is lambda times lambda minus 1. And this is equal to 0 when say lambda 1 equals 0 is one of my eigenvalues. And I'll call lambda 2 1, right? 1 is the other eigenvalue. Okay, so here are the eigenvalues of this matrix of coefficients, this matrix A. Then I find the corresponding eigenvectors. All right, so first with lambda equals 0 means I'm solving A times some vector k equals the 0 vector. You need to find some non-zero vector k that makes this true. A minus lambda I, or A minus 0I, times vector k equals 0. So really here I'm just going to be putting matrix A, 3, negative 3, 2, negative 2 here. I'm just going to put this one into reduced echelon form, reduced row echelon form, which is pretty quick and simple. I'd have to multiply the top equation by negative 2/3 and add it to the bottom, and that would make the bottom into zeros. And multiply the top equation by 1/3 to get that leading 1. Alright, and then say vector k here is made up of components k1 and k2. So in this case, k2 would be a free variable. I'll call this t for some real number t. I can let it be any real number I wish. And then from the first row, we got this equal to 0. k1 minus k2, k1 minus t equals 0. So k1 would be equal to t as well. And so my solutions, right, these vectors k that would make this true, would be t times the vector 1, 1. And so the simplest of these, which I'll call k1, would be just the vector 1, 1. All right, and we're getting from this, a solution to the non-homogeneous equation would be x1. All right, I'll call this x1 because it corresponds to lambda 1, equals 1, 1, our eigenvector k1 here, times e to the 0t. Well, e to the 0t is just 1. So just the vector 1, 1 is this x1. Okay. And now I do the same thing for lambda equals 1. Right. So for lambda 2 equals 1, and again, if I feel like I'm sorry if it feels like I'm rushing through this, but I'm assuming you know how to do this. So I'm kind of going pretty quickly here. All right. I'm hoping you've seen previous videos on solving homogeneous systems. So we're solving this equation, a minus I, right, a minus 1I, times some vectors k equal, when z equal to 0 vector. Now a minus I would be this matrix 2, negative 3, and negative 3, and 2, where the first row and second row are the same. Put this into reduced row echelon form, with a calculator if you want, or this one's easy to do by hand. Just take the opposite of the first row, add to the second row. The second row will be a row of zeros. Then multiply the first row by a half. Say 1 here, negative 3 halves there. And again, k2 would be a free variable, and because of the half in the denominator there, I'm going to put make that 2t for some real number t. And then this would imply the first equation that, set that equal to 0. k1 would be equal to 3t if k2 were 2t. And then, so my vectors k that satisfy this equation are t times the vector 3, 2. And the simplest of these, which I'll call k2, right, because this is lambda 2, is the vector 3, 2. Right, and so another solution to our homogeneous system, right, this corresponding homogeneous system, which I'll call x2 because it's coming from lambda 2, is the vector 3, 2 times e to the lambda t, e to the 1t. Right. So here's my, it's a 2 by 2 system. I should be finding 2 linearly independent solutions to it, and I have. So here's my fundamental set. All right, the fundamental set of solutions to this corresponding homogeneous system is the set consisting of these vectors. x1 was just the vector 1, 1, and x2 was the vector 3, 2 times e to the t, or you could say 3e to the t, 2e to the t, right, that vector. So again, this is x1, x2, and they're 2 linearly independent solutions to our homogeneous. So our complementary function, right, xc, the general solution, right, the general solution to our corresponding homogeneous system is some constant, say c1, times x1, so times 1, 1, plus and some constant c2 times x2. Right, so 3, 3, 2 times e to the t. Okay. Again, as I mentioned a second ago, well, not a second ago, like 10 minutes ago in the talking about, setting this up, you could write this as a matrix statement, right? So, and sometimes I have my matrix with square brackets or parentheses, it doesn't matter. Right? Where this is 1, 1 down the first column, and then 3 e to the t, 2 e to the t down the second column. There's x1 down the first column, x2 down the second column, and then times c1, c2. The constant a column vector with the constants, with the coefficients. And this is what I had earlier. This matrix here, where each column is just a vector from the fundamental set of solutions to that corresponding homogeneous system. This is the fundamental matrix for our system. Again, fundamental matrix, right? Which I'm calling, I was calling phi of t. Right. Okay. And then this was that c vector, that vector of constants. Okay, good. So now I have, the complementary function. I'll put it in a little bubble. This is going to be part of the final solution, right, when I write out the general solution to the non-homogeneous. All right, so next comes the variation of parameters part. Right. So that's probably going to take the longest. The next part is the variation of parameters. I guess it's step 2, right? So I take these parameters, these arbitrary constants c1 and c2, and I let them be functions that vary with t. Call them maybe u1 and u2. And we get the form of a particular solution to the non-homogeneous system. So the form of a particular solution will be the following: xp equals phi of t, our fundamental matrix, so this one again, times u of t, where u of t is again some vector with functions u1 of t, u2 of t. All right, and there we go. All right. Now remember, I showed you a formula for this, right? You don't have to do all the substitution that I did earlier, right? I did this at the beginning of the video. This u of t is the following. Here's how you find it. So u of t is the integral, and don't worry about constants of integration at the end, like with variation of parameters for a single equation, of phi inverse times function f, vector f, and then with respect to t. Now going back to the beginning of the problem, vector f, very beginning, blah blah blah, vector f was this vector 4, -1. All right. So vector f is this vector with components 4, -1. And phi was the fundamental matrix. Now it's only a 2 by 2 matrix, so finding the inverse isn't going to be terribly difficult. Right? So let's get that here. So phi, right, is equal to this 1, 1, 3 e to the t, 2 e to the t. Remember, you can find the inverse pretty quickly. I'm assuming some basic linear algebra knowledge here, so finding the inverse of a 2 by 2 matrix shouldn't be terribly difficult. First, I would find the determinant of phi, which would be 2t minus the 2 e to the t minus 3 e to the t, so it's negative e to the t. And then we take the reciprocal of this and multiply it by the adjoint matrix, which for a 2 by 2 means just switch these two and then take the opposites of these, right? So phi inverse is negative e to the negative t, right? That'd be the reciprocal of negative e to the t, right? Negative 1 over e to the t, or e to the negative t, times the matrix where I switch these, 2 e to the t here, 1 there, and then take the opposites of these, negative 3 e to the t and negative 1. And if we multiply each component in here by negative e to the negative t, we get the following. So phi inverse looks like this. We have negative 2, right, because e to the negative t times e to the t is 1. Positive 3, there's the first row. And then we have positive e to the negative t and negative e to the negative t. Great. All right, so what I'm doing now is I take phi inverse times f, and I'm going to get a 2 by 1 column vector, and then we're just going to integrate each column, each component of that vector, component by component. All right, so I'll take phi inverse times f. All right, so that's this negative 2, 3, e to the negative t, negative e to the negative t, times vector f, which is this 4, negative 1 here, and we're getting another 2 by 1, right? So it'd be negative 8 plus negative 3 is negative 11 for the first row, first column, and I probably should have left more space here. Well, not really. I can do this in a small slot. I have 4 e to the negative t plus 1 e to the negative t. That'd be 5 e to the negative t. And then we integrate this component by component, and that gives us our vector u. Right. So again, this vector u of t is the integral of phi inverse times f with respect to t, which if you integrate each one component, it'd be negative 11t. And don't worry about the constants of integration. You can just have the constant be 0, right? It's just like variation of parameters with a single equation. And this one would be negative 5 e to the negative t. Right. And there we go. Okay, wonderful. All right, so then, finally, a particular solution to our non-homogeneous system. Remember, the form that takes was phi, right, the fundamental matrix, times u. So this is u, and then phi, right, was our fundamental matrix from earlier, this here. Right. So this is this 1, 3 e to the t, 1, 2 e to the t, times u, which is this negative 11t, negative 5 e to the negative t, and again it's a 2 by 2 times a 2 by 1, so the result will be a 2 by 1. Right. And we have negative 11t, negative 11t minus 15 for the first component of our particular solution. Okay, and then negative 11t then minus 10 for the second component of our solution. And then we're almost there. Because now we have a particular solution, and we have our complementary solution from earlier, this thing. Right. And we can write this all out now. Now if you'd like to separate this, we could write this as t times the vector, negative 11, negative 11, right, plus the vector negative 15, negative 10. If you want to spread it out like that. There's nothing wrong with keeping it as a single vector like this, though, right, or the sum of two vectors. So then finally, right, the general solution of our homogeneous system is the following. I can replace x with, xc, right, xc, so any some constant times the vector 1, 1 plus some other constant c2 times, the vector 3, 2 times e to the t, and then plus our particular solution. Right? And our particular solution looked like this. The vector -11, -11 times t plus the vector -15, -10. Or if you wanted to write that all as a single vector, that's fine. All right, and this will be a solution. This gives us solutions to this system. All right, going all the way back. I know this is a lot of writing, but going all the way back to our original system, which looked like this. Where was that? Lots of stuff, Jeez. Okay, there it is. Going all the way back to this original system here, there's a description of every possible solution to that system. You just replace C1 and C2 with anything you want. All right, and I'll leave it to you to verify. I think the easy ones would be just replace C1 with 1 and C2 with 1. All right, just check those. Or you could replace C1 and C2 with any numbers and verify, again, that we have a solution to our system here. Okay? All right, so again, you can see how long this can take. And I've got just a couple more. All right. But the procedure doesn't change. First, you find the solution, the general solution to the corresponding homogeneous system. Then you find, a particular solution, which will be that fundamental matrix phi times u, where u is the integral of phi inverse times f with respect to t. All right. And then you put it all together. So again, I know it sounds simple when I say it like that, but you've seen from just this example that it can take a pretty decent amount of time. All right, so here's another example. Now this one's already written in matrix form. So I've got x prime here, which will have dx dt dy dt, or x prime y prime. You want to call the functions x and y. Equals this 2 by 2 matrix A times vector x here, and then this is the vector f, which has e to the half t and then negative e to the half t. All right, so let's start off with the homogeneous version, right? The corresponding homogeneous. Let's solve that and find the fundamental set of solutions to this homogeneous, which will be help me form the fundamental matrix phi. And then I can go to variation of parameters and find a particular solution to the non-homogeneous system. So x prime equals a, let's say a times x. So let's find the eigenvalues. Let's find the eigenvalues of a. All right, so I'm solving again this equation. When is the determinant of a minus lambda I equal to 0? So this is 3 minus lambda, -1 minus lambda down the main diagonal, and then -5, and then 3/4 down the other diagonal. All right, now this is lambda squared, all right, and plus lambda minus 3 lambda, that'd be minus 2 lambda, then minus 3, and then plus 15/4. Right, and we're trying to see when's this equal to 0. Okay. Now -3 plus 15/4. That'd be -12/4 plus 15/4. That's plus 3/4. Right, so this is lambda squared minus 2 lambda. Then this is again -12/4 plus 15/4. That'd be plus 3/4. Equals 0, and I'm going to solve this by completing the square. So I'll add 1 to both sides, right? Subtract the 3/4, that gives me lambda minus 1 squared equals, and then 1 minus 3/4 is 1/4. So I'm getting one solution is 1 plus a half, so 3 halves. And another solution is 1 minus a half, right? The square root of a quarter would be a half, and then 1 minus a half is 1/2. All right, so one eigenvalue is, lambda 1 equals 3 halves. Another eigenvalue is lambda 2 equals 1 half. So again, I have a case where I have distinct real roots. Just know that that's not always going to be the case. You might have roots with multiplicity of 2, or maybe you'll have even complex conjugate roots, and hopefully you've seen my other videos on those scenarios. Alright, so now we're going to find the eigenvectors corresponding to these. Alright, so eigenvectors. So first for lambda equals 3 halves. So I'm solving this equation, a minus 3 halves I times some vectors k, when's this equal to the 0 vector? Where, again, let's say k has components k1 and k2, right? These are 2 by 2 matrices here. So that should be a 2 by 1 column vector. This matrix, just take matrix A and subtract 3 halves. So that's 3 halves down there, and then negative 1 minus 3 halves would be negative 2.5, negative 5 halves there, and then you have negative 5 here, and 3/4 there. Alright, and then I wish to put this into reduced row echelon form. If I just multiply the top by negative half and add to the second row is 0, and then I multiply the top by 2/3, you get 1, and then negative 10/3. Alright, there's the matrix in reduced row echelon form. Again, you can use a calculator. Most of these 2 by 2 should be pretty easily done by hand. Okay, so k2 is a free variable. I'm going to have k2 because of this denominator of 3 here. I'm going to let k2 be 3t for some real number t. And then, saying the top, you have k1 minus 10/3 k2, or minus 10/3 times 3t minus 10t really, equals 0. So k1 would be equal to 10t. And so the solutions to this equation are t, some number t, any number t, times the vector 10, 3. Alright, so k1, the simplest of these, is the vector 10, 3. And x1, right, a solution to this homogeneous system would be k1, 10, 3, times e to the 3 halves t. Alright, times e to the 3 halves t. So there's part of the fundamental set. That's not the answer. I'm just putting in a little bubble. Alright, then I do the same thing for lambda equals a half. So again, solving this equation here, what a minus a half I times some vector k equals the 0 vector. So again, matrix A minus a half down the diagonals. So that's 5 halves, and then negative 1 minus a half would be negative 3 halves. Then we have negative 5 here, 3/4 here. Alright, now again, I want to put this into reduced row echelon form. Again, you should be able to, if I were to multiply this by, negative 3/4 times 2/5, basically. Negative 3/4 times 2/5 would be negative 3/10. If I multiply the top by negative 3/10, yeah, you'd get 3/4, negative 3/4, positive 3 halves, and add it to the second row. The second row would be made up of zeros. And then I multiply the top by 2/5 to get that leading 1, and this times 2/5 would just be negative 2. Right. And then again, we have k2 is a free variable. I'm going to let that be t for some real number t. And then we have k1 minus 2t equals 0, so k1 would have to be equal to 2t. And the solutions here would just be some number t times the vector 2, 1. So the simplest of those, I'll call k2, because this is lambda 2, is the vector 2, 1. And then our second solution in the fundamental set, x2, would be the vector 2, 1 times e to the half t, or t over 2. So I'll bubble this. Alright, so I'm not going to write the fundamental set out again. I'll just say, hey, there's one vector from the fundamental set. There's the other vector from the fundamental set. So now we can state our complementary function, right? any linear combination of those. Right? Any linear combination of those is a solution of our homogeneous equation. So xc is some constant c1 times x1 times the vector 10, 3 times e to the 3 halves t plus some constant c2 times, and then x2 times the vector 2, 1 times e to the half t. All right, and as I said before, you can write this as a matrix, matrix product, where I have 10 e to the 3 halves t, 3 e to the 3 halves t. Right, this is x1 down the first column. x2 is 2 e to the half t, and then just e to the half t down the second column. And this is the fundamental matrix. This is phi of t here, times the constants, right? C1, C2, right? And this is just that vector of constants, which I called capital C before. All right, so I'll put this in a nice colorful box because I know this is going to be a huge part of the general solution to the non-homogeneous system. Okay. All right, now for our particular solution where we vary the parameters, right? Here comes the variation of parameters. I replace this vector c with a vector u with functions u1 of t, u2 of t. Let these, be, instead of be constants, let them vary with t, and we get the form of a particular solution. All right. So a particular solution is going to take the following form. So the form of a particular solution, xp, is going to be, phi, this fundamental matrix, times u, where again u, I have to find this way using the integral of phi inverse times f, and with respect to t. All right, so I gotta go back and remember what f was. Right? F was way back here. Right? F was this vector. Was, I'll say e to the half t, negative e to the half t. Right? I'll write it as a single vector there. So e to the half t and negative e to the half t. Right? There's vector f. All right, now I know what phi is. Right? We got it here. So now I need phi inverse. Right, so I'll leave phi up there. Now I need the determinant of phi if I want to find phi inverse using, like the adjoint matrix method. So this would be 10 e to the 2t, right? 3 halves t plus 1 half t. 10 e to the 2t minus 6 e to the 2t. So that'd be 4 e to the 2t. So putting this together, phi inverse is, the reciprocal of this would be 1/4 e to the negative 2t. That'd be 1 over 4 e to the 2t. Times, and then the adjoint matrix, remember for a 2 by 2 it's easy, you just switch the main diagonal entries. So e to the half t up here, and then 10 e to the 3 halves t here, and then take the opposite of the other two, right? So negative 2 e to the half t, and then negative 3 e to the 3 halves t. Okay, there's phi inverse. All right, now what I'm going to do is, I want phi inverse times f, and then we'll integrate with respect to t component by component. All right, so I'd have this quarter e to the negative 2t out here, and then this 2 by 2 matrix times a 2 by 1 vector f will be a 2 by 1, where I take, first row with first column. So this would be what? E to the t plus 2 e to the t. So that'd be 3 e to the t right there. And then second row, first column, I do the dot product of the second row with the first column here. We'd have negative 3 e to the 2t minus 10 e to the 2t. So that'd be negative 13 e to the 2t. And then multiplying by this quarter, e to the negative 2t, I get phi inverse times f is 3/4 e to the negative t, e to the negative t, right. And then negative 13/4. There's phi inverse times f. And then for u, we're integrating component by component, right? So this u of t is, again, the integral of, phi inverse times f with respect to t. So we got here, and again, ignore the constants of integration. So this would be negative 3/4 e to the negative t, and then negative 13/4 t. All right. Great. Then I multiply this u by phi, and I get my particular solution to this non-homogeneous system, right? Lots of work. In fact, I know I said I was going to do 3 examples at the top of this video, but after doing these 2, I think I'm going to stop here. All right, we'll finish up with these 2 examples. So I apologize if you were hoping for 3. I'm sure you're going to be okay with that. This is almost an hour now. So xp, the particular solution that we're going to find to our non-homogeneous system, is phi. Right. Now phi was this. You had 10 e to the 3/2 t, e to the half t down here, and then positive 2 e to the half t, and then positive 3 e to the 3/2 t. Right. This was phi. Pretty sure. Let's make sure, doubly sure. Yes, all right, and then times u, right? Phi times u for this particular solution, right? Phi times u. Times u, and u is this, negative 3/4 e to the negative t, and then negative 13/4 t. All right, so again, I have a 2 by 2 times a 2 by 1. This is going to end up being a 2 by 1. All right, so we have here 10, so negative 30/4. Well, that simplifies a bit. So negative 15/2. All right, negative 15/2. And then e to the 3/2 minus 1 is just 1/2, so e to the half t. And then plus, negative 13/2 times t, e to the half t. All right, there's the first function in the particular solution. Right? And then the second function, or the other function that's part of the particular solution here, taking the second row, first column here, we have negative 9/4 e to the t, e to the half t again. Right? And then minus 13/4 times t, e to the half t. All right. And again, you can split this up if you wish, and I'll do it when I write the general solution. But now I have a particular solution. Again, I'll bubble this, a different color here. No, that's part of the final solution. All right, so our general solution, finally. All right, these take a bit. So our general solution, and to the original non-homogeneous system, right, going all the way back to this system. Our general solution x is the following. It is the complementary function, right, the solution of the general solution of the homogeneous. So again, I'll write it this way, and I'll write this out here. Sorry about this. So the complementary function, so it's some constant, right, times the vector 10, 3 times e to the 3/2 t plus some other constant c2 times the vector 2, 1 times e to the half t. All right, there's the complementary function plus our particular solution. Now again, I'm going to break this up. So I got the vector negative 15 halves, negative 9 fourths, and both of those are times, e to the half t, plus the vector negative 13 halves, negative 13 fourths, times, both of those are times t e to the half t. And there we have it. All right, putting it all together. Right, that's it. Final solution. And again, if you wish to verify this, all right, and I'll leave it to you. I'm not going to waste more time. Go back to the original system. All right, go back to the original system, and use this as x, find x prime, substitute, and see that indeed the equation will be true. And I'll telling you right now, it will be true. All right, as ugly as it looks, it does work out. Okay, wonderful. All right, so yeah, a lot of work on that. As I said, I'd meant to go over a third example, but kind of almost running an hour here. And it's the same procedure, it really is. It just, the function, the vector f will change. That's, the vector f changes, your fundamental matrix phi changes, of course, depending on how the system looks. But the procedure is the same. Right? So first you find the complementary function, that xc, you find the solution, the general solution to the corresponding homogeneous system. All right. And once you find that, you'll also be able to determine, that fundamental matrix phi of t. All right, then you set up your particular solution, which will be phi of t times some vector u of t, where u of t is the integral with respect to t of phi inverse times f. All right, then once you find u that way, you multiply by phi, you got your particular solution, and then the general solution is the complementary function xc plus the particular solution xp, that phi times u. All right, so I did the same procedure, the same order, both of these examples, and I would do it with a third example or whatever other example I had with a non-homogeneous system. It's just, again, the vector. So far my vectors f were constants and exponentials. They might have trig functions. They might have other functions. So just pay attention, and it's going through the same steps every single time. All right. And I'm hoping that watching me go over these couple examples and describe the procedure of variation of parameters, I hope this all helps you when you're working on this stuff, something similar to this on your own. And thank you very much for watching.